Hi, so we are doing homework for Part C for Process Dynamics and Controls. Today we are going to have a little introduction to what a Smith Predictor is, how that can control a system and help with our dead time. So I'm going to go ahead and derive some things, show you some things, and get into all that. To start off, we are going to go ahead and draw and explain a block diagram for a general Smith Predictor controlled system with dead time. What a Smith Predictor does, essentially it removes delay from a feedback loop so the controller behaves as if there's no dead time at all. It uses a model that I'm denoting GP with, I forget what this is called, but the little squiggle character above. And it uses that to predict what the output should be at a point in time. In order to decrease the effective dead time. So what we would have is we would have some set point going into our system. We would have a comparator here, and this goes into our transfer function GC, which then goes to our process transfer function GP, so GC is for our controller. GP will also go into a comparator, and what we will have is some disturbance. We'll call that GD, and we will be output with our Y. And now we are getting into the Smith Predictor. So we have our GP with the little squiggle on top. That is our model to predict with. And so we have that there, and it is attached to that comparator that you compare with the set point. And this Y is just whatever value you're measuring. So in the past we've done a lot with like liquid level height, so that could be height, temperature, any of those things. And then we are looking at dead time, so we need to compensate for that dead time. This also goes to a comparator, which is connected to this line up here. And it looks like I actually forgot one extra comparator. So we have our set point going into that one, and we need to compare our model to what is actually coming in. So up here in the top, we have our system with no dead time, but we use our Smith Predictor here to account for dead time. And basically this is used to try to get rid of the effects of dead time. So you can kind of think of it like this. If you're driving your car and you're steering the wheel, let's say there's a pothole in front of you and you're trying to swerve to the right to get away from it. Obviously you want the dead time to be very short. But if for some reason your system had high dead time and you turn your wheel and your tires don't turn quick enough, then you're going to hit that pothole. So this would be a way around that. It would treat as if there was no dead time, and it would have this Smith Predictor to compare to our output, or to compare to our input, our set point, so that our car would be able to steer. Now we would like to derive the closed loop response of a Smith Predictor controlled system to changes in set point and disturbances. So changes in set point here and our disturbances. So our simplified block diagram, since the previous one was a little bit intense, we can draw it like this. We can have our GC divided by 1 plus everything in the forward direction, which would be GC, GP with the little squiggly, times 1 minus e to the negative theta s, and that squiggle should be on the theta and not the e. So this right here is everything in the loop going here. And that's still going to go into our process transfer function GP. We still have our disturbance GD. We have our comparator, our output Y, and then we need to compare these values still to the set point so that we can make any changes necessary. So our output Y is equal to D times GD, so our disturbance times the transfer function of our disturbance, plus our set point minus our output Y multiplied by GC GP divided by 1 plus GC GP with the little squiggle times 1 minus e to the negative theta s. And I'm going to go ahead and label this entire thing as GN just to simplify our writing a little bit. And then we get y times 1 plus gn is equal to d plus the set point times gn. And through some manipulation, we can get our y is equal to the disturbance times the transfer function of that disturbance plus the set point times our gn, so our general transfer function here, and that's divided by 1 plus gn. And so this right here is the closed loop response to changes in the set point as well as the disturbance. Next, I'm going to go into code to simulate a closed loop response of a first order system using an imperfect Smith predictor and compare that with a closed loop system such as this. So what we're going to do is simulate the closed loop response of a first order system with gain of 1, time constant of 2, and dead time of 10.5 seconds, so pretty significant dead time, using an imperfect Smith predictor model with a gain of 0.95, time constant of 2.2, and dead time of 10 seconds. And then we're going to compare that with the response of a closed loop system with dead time compensation, and we will be using a proportional and integral controller with a controller gain and reset time, a controller gain of 5 and a reset time of 10. As always, I have my import up here. We said our KC was 1 and our tau is 10. And this tau is the reset time that I just talked about. Our GC is equal to KC times 1 plus 1 divided by tau times I, tau I times S. And our controller gain is 1. The above our KC was 1, that was our controller gain. This right here, K, is the process gain. Our tau is 2. And our theta, or our dead time, is 10.5 seconds. Our Smith predictor, I'm going to denote with an underscore after. That is going to be 0.95 for our process gain. The tau is 2.2. And our dead time is 10 for our Smith predictor. I need to put the underscore. So our theta underscore is 10. Our transfer function then with the dead time is K times e to the negative theta times s divided by tau times s plus 1. And our model with the Smith predictor is going to be our K underscore divided by tau underscore times s plus 1. And now we want to go ahead and simulate. We have GC times GP divided by our 1 plus GC times GP. And we want to make our subplots. X is equal to time, y is equal to y from here. And our mode is lines. I'm going to set a width and a height. And obviously we want our figure to show. So I'm going to run this and see if it gives me something. So that graph that you just saw was not correct. However, it's because I made this controller gain 1 instead of 5, which is what I was supposed to do. And then after fixing that, we can see our graph right here. And what we can see here, our x-axis is the time and our y is our output, and we are reaching thousands, which is obviously not correct. It's very unstable, and this is likely due to our large dead time that we have, as well as the mismatch between our actual parameters and our Smith predictor parameters. And now what we want to do is compare with the response of a closed loop system without dead time compensation. I'm going to call this M, and that is equal to GC times GP divided by 1 plus GC times GP underscore times 1 minus e to the negative theta s. We have T y is equal to the sim of m divided by 1 plus m. Actually, I should be using my gn that I defined earlier, so let me change that. We have our lambda, our n, and dt. Our disturbance, we're going to set equal to GP, and then our ty disturbance is equal to the sim GD divided by 1 plus GN. lambda t divided by 10, and the t over 10 is ramping our disturbance over time. If we are under 10 seconds, otherwise it's 1.0. Set our n and our dt. And then we want to make subplots and add a scatter of x is equal to t, y is equal to y servo. We have lines, and the name is the servo. And we also want to do our disturbance right there. And we want to show that figure. And I spelled lambda wrong, so. And this theta is supposed to be the Smith Predictor theta, so I had that wrong. And in our graph, we can see essentially this red is our disturbance. It doesn't kick off until our dead time, our actual dead time of 10.5 seconds has passed, because you can't get around that. Same with our servo. And it peaks and it decreases because the system is reacting actually to this disturbance now because of our Smith predictor. So after our initial dead time has passed, we immediately shoot up, and obviously we have some oscillations, and you can see there's a bit of a pattern. This is due to, like I was saying before, our actual parameters and our Smith predictor parameters are not the same. So we have some oscillations there, but as you see over time, that decreases, and we're landing around 1. So that's a good thing. So if I were to go up here and set these equal to each other, rather than having a mismatch, we can run it, and then we see we don't have those oscillations anymore. So it all kind of depends on how accurate your Smith predictor is, but even when it wasn't exactly correct, it was still pretty close. So if I make it different but closer than before, we have those little spikes, but they go away faster and they're smaller. And these spikes happen after each 10.5 seconds has passed. Thank you for watching. In the next video, we are doing cascade control, and that's going to be the final part for this class. So look forward to that.